Brian holds the field professorship of nuclear environmental engineering and sciences in the Department of Environmental Engineering and Earth Sciences at Clemson. He previously held postdoc appointments at the Livermore Lab and the Berkeley Lab. He has a Bachelor's of Science degree in chemistry from the University of Montevallo, master and PhD degrees in environmental engineering and science from Clemson. In addition to his studies or his duties at Clemson University, Brian also serves on the Radiation Safety Committee of the US EPA Scientific Advisory Board. He's a member of the National Council on Radiation Protection Program Activity Committee 5, environmental radiation and radioactive waste issues, and holds a joint appointment with the Savannah River National Lab. Brian is the 2018 Fred C. Davidson Distinguished Scientist from the Citizens for Nuclear Technology Awareness, the 2018 McQueen Quattlebaum Award winner from Clemson University, and the winner of the 2014 South Carolina Governor's Young Researcher Award for Excellence in Scientific Research. He has published more than 70 peer-reviewed journal articles and has garnered over $17 million funding from various agencies. So a very, very successful young fellow. So the podium is yours. Brian's going to talk to us about geochemical modeling.
Thank you very much. That's probably the nicest introduction I've ever had. I'm Brian Powell from Clemson University and 1 day a week from Savannah River National Lab. I'm going to kind of stick to the title of this talk. I'll show some models. But when I started looking at the agenda, we have a large team of collaborators, as you can see from the co-author list. We're really looking at using some imaging technologies on relatively small scales. So we're talking in our lab on, microscopy of particles down to column scales, and field columns maybe about 2 feet tall. And so we're going down to a scale I don't get the impression a lot of people in the room necessarily work on. But what I'll point out is earlier there was an excellent comment made about, when we go up to these larger scale models, there's not that many knobs to turn. I believe it was you, sir, that made the comment. There may not be that many knobs we have to turn to adjust the model to really drive these models and find the most important factors. And what we really strive for in the experiments that we run are lab scale columns and kind of intermediate field scale experiments. And what we're trying to do is define those reactions, find those key pieces that are really controlling the mobility of each of the radioisotopes, and get some sort of quantitative model behind it, preferably not an empirical KD at the end of the road if we can do that. So I'll show this using 2 examples. One with some field experiments that are being done here at the Savannah River site, looking at neptunium and plutonium transport. And then I mentioned we're using a lot of medical imaging techniques, and I'll show an example where we're monitoring technetium transport on the laboratory scale and using that to explain the data from the field dosimeter experiments. So a field dosimeter is essentially a large soil column that we put out in the field and let it get rained on. Rainwater percolates through it. There was a series in the 1980s that were done here at Savannah River that there's been a number of publications come out on, particularly looking at plutonium geochemistry. And those are actually buried underground with a pump at the bottom that would pump the water back up. And in 2011 or so, we approached the site about burying sources again, and they explained they already have enough buried radioactivity on site and they don't need any more. So we went and bought dumpsters and put them above ground. These really are 8 by 8 by 22 dumpsters. This would show up if you were doing construction on your home. And inside them, there's an I-beam, two I-beams, welded down the center. And then we attach these secondary outer housings to them. And then we can lower down an inner pipe that has flexible tubing in it that can be plumbed out, a hole in the wall that you can see in this upper left image coming out, going into boxes where we can collect the water. So we can go and place a column. If you look in the upper right-hand corner, or your upper right-hand corner, excuse me, we can pack a column in there with some soil from wherever we want to get it from, put a source of a radioisotope in, put soil the rest of the way up, and then deploy the system out into the field and let it be exposed for as long as we want. We've had these go out for as little as 9 months, and now as many as, we're up to about 6 years for the plutonium sources that are out now. This facility here is out near the Bay Area wetlands. For those of you familiar with the site, here it's quite literally outstanding in its field. This facility that you're looking at here is in our backyard at Clemson, and the only difference between the two is these are very highly, you can see these, there's several different pieces here. We've got a lot of real-time monitoring equipment built into the one at Clemson, mainly because we have access to power and water right next to the building for it. And so what we put in is something that looks like this. I'm going to focus on plutonium-neptunium lysimeters. This is a 2-inch diameter filter paper, and two filter papers. In between it is somewhere between 2 to 10 milligrams of a plutonium or a neptunium solid source. We start with different phases. This is a radiography image over on the right that you can see that nice green color of a plutonium oxide material there shown over on the right. So we take that source, recall, is buried somewhere in a lysimeter. So this is about a 2-foot tall lysimeter. We take them out of the ground, we put them in a HEPA filtered box, and we slice it open longitudinally so we can open it up and then essentially take a paint scraper that we turn into a guillotine and slice it into centimeter thick sections that then we can isolate concentration profiles as a function of distance. But the more important thing is when we can see the whole area in front of us, it's relatively easy to make sure we don't damage that source. Because the critical piece is finding the source afterwards and seeing how it's changed over time, at least in our minds. So our approach is we deploy these in a variety of sources. We're most interested in plutonium, but then we deployed some neptunium sources for comparison. Right now, we've pulled an entire series of these out, about 7 lysimeters after 2 to 5 years of exposure. They're all deployed in triplicate, so we'll be able to go for each of the sources, so we'll be able to go look at them. And then we carry it through a large series post-characterization. We started with a plutonium-5 ammonium carbonate, a plutonium-3 oxalate, plutonium-4 oxalate, plutonium-4 oxide, and then a neptunium-5 nitrate solution and NPO2 as our sources. The mobility of actinides is absolutely driven by what oxidation state they are in. So having different initial oxidation states of plutonium is critical to be able to monitor this. We've spent about the last 15 years or so showing how dynamics of oxidizing rainwater coming in and then reducing conditions going back into a system can actually cause a dynamic movement of plutonium through the system. But neptunium provides a nice comparison because neptunium-4 is relatively unstable in the relatively low pH oxic vadose zone of the Savannah River site. So this should oxidize to the more mobile neptunium-5. Conversely, all of these states of plutonium-4, even in the oxalate, will eventually auto-reduce to PuO2. It's one of the more stable phases on the planet, to be honest. So we expect transformation going in opposite directions of these. Neptunium to oxidize, become more mobile. The plutonium to reduce and become more immobile in this. And so we can test that readily. As I mentioned, we carry these out. We pull samples from the effluent. These are the pipes coming out in collection bottles, and monitor those quarterly to be able to see what's coming out the bottom in a mobile aqueous form. So the work I'll show you, and just for the reference of the printed notes I've provided there. But as I mentioned, our key hypothesis in this is looking at this transformation. We believe everything should convert to PuO2 type phases over time, and the Neptunium-4 should oxidize to Neptunium-5. And it's interesting, we want to compare it to some work that's already been done. This is an outstanding paper that was published looking at plutonium and uranium sources from a bunch of different field sites. And what they went in and said is, essentially in this conclusion is, well, they know there's some thermodynamic gradient to form an oxide phase, but they don't really know what the starting conditions are. You know, for the most part, the large holes in the ground that DOE poured waste into, we have a kind of an idea of what went in there, but not necessarily. And so in these lysimeter experiments, we actually have the chance to know what the initial conditions were very, very explicitly, because we're the ones who buried it ourselves. We don't have to rely on historical records of this. So, skip this for now. So this is an example of one of the profiles that can get developed from these. What we're looking at is a concentration in the soil normalized to the concentration of the soil at the source as a function of depth in the lysimeter. And I'm just plotting 0 and down, and mainly because right now I don't want to have to explain the fact that plutonium will also move upward, not to the same extent, but to some degree. And what we have here is 2 plutonium-5 sources. One of them, lysimeter 41 here, was not amended with any material. In number 22, we actually added a layer of organic matter that can form complexes with plutonium and either enhance its mobility if it's more soluble, or in this case, it retarded the mobility. You can see that that blue line, the organic matter-free plutonium, was moving much further down in the lysimeter than the organic matter. So we actually believe it was sorbing, the organic matter was coating the surface of the soil and holding the plutonium with it. So we're going to look at a bunch of different profiles, and there's a lot going on in the data. And so what I'm going to do is I'm going to put the things I'd like everyone to remember in your upper right-hand corner with this. So right now we got organic matter retards plutonium transport. And then if we look and compare this to a lysimeter, this is data from the 1980s lysimeters that were done at Savannah River, where plutonium-6 was the initial oxidation state. We see transport of that plutonium-5 pretty comparably to the plutonium-6 phase, showing that the relatively similar mobility of those oxidized forms of plutonium. And then if we look at a plutonium-4 source that we expect to be this very, very immobile source of plutonium, and the blue lines with diamonds here, we can see it's quite similar to our initially plutonium-5 source that had organic matter amended into it again. So it does appear indeed that the organic matter is not only enhancing absorption of the plutonium to the soil, but it's possibly enhancing that transformation down to a PuO2 type phase. So we took the samples and went and did X-ray absorption spectroscopy on them, and the spectra are shown here. This is the first derivative fit in your lower right-hand corner of the data. And what it shows essentially is that reduction of plutonium from 5 to 4 is very enhanced in the field. Roughly 93 or 85% is plutonium-4 in the field-deployed samples versus about 65% in the archive samples. We can't stop this from happening. It's a thermodynamic gradient. It's going to go to PuO2 phases no matter what. But it does appear to be accelerated, at least for these 2 data points that we have in the data. If we look at the actual structure, the fine structure of these, they're very, very disordered phases. One of the critical pieces is the differences between a perfect crystalline PuO2 structure and the bond lengths and coordination numbers that we get for these materials show they have an extraordinarily high degree of disorder to them owing to the formation in the field. So it calls into question what fundamental Gibbs-free energies of those solid phases do we need to use when doing speciation modeling if we have that degree of disorder with this. They do all appear to be solubility controlled. These are the values for the aqueous plutonium coming out the bottom of the lysimeter. They all range down on the order of solubility controlled phases, which is not terribly surprising to at least it wasn't to us. What we do need to confirm is that this is indeed transport of an oxidized form of plutonium coming in from the rainwater in these data. These are just concentrations not any particular chemical speciation was done. So if we compare this now, we have a system where all the plutonium is going to a plutonium-4 source. It's reducing and it's not moving in the environment. We can have a kinetic model that we've put together looking at this very slow reoxidation that causes mobilization of a concentration of plutonium that's essentially below solubility limits. And so for the modeling work, it's a relatively simple system. We can just say it's controlled by solubility and it's got a really, really high KD, and generally plutonium doesn't move. The other critical piece of the experiments I didn't point out is those lysimeters were deployed 5 years, 99% of the plutonium stayed within 1 centimeter. The lysimeters deployed for 12 years, 99% of the plutonium stayed within 2 centimeters. So it's not terribly mobile. That's not really surprising, and I don't think it's a terribly surprising result. What we thought was really interesting in this is the comparison with the neptunium. So the upper right graph is showing 2 similar neptunium lysimeters. They both had neptunium as a neptunium nitrate solution just pipetted onto a filter paper. And what it's showing is cumulative activity coming out in the bottom of the lysimeter as a function of the volume that went through. These are supposed to be duplicates. They were prepared exactly the same. They were literally side by side in the lysimeter, and yet you can see some rather large differences in those. It's actually to kind of keep that in the back of your mind. We believe due to preferential flow, and we'll show you some data to prove that soon. Remember, we got a 4-inch or a 6-inch diameter pipe and a 2-inch diameter filter paper. So if all the water goes along the side of one pipe, it's not going to interact with the source at all. So those flows really are absolutely critical in this. So, but these are concentrations coming out. It's showing that roughly somewhere in the, in the area of 5 to 30% of neptunium is coming out the bottom of those. If we then add on to the plot the source from a neptunium-4 lysimeter, the insoluble form of neptunium, we're still 10 to the 11th, 10 to the 12th. So we're well over where the plutonium was, but it's still quite low. And again, we didn't measure the oxidation state, but we believe this is the beginnings of neptunium-5 that's oxidized off that NPO2 surface coming out. And so if we go look at the profiles, again, this is measuring distance from the source, starting from 0 at where the source is, going down. We can see a steady concentration in the triangles of the neptunium-5 source. That's pretty well, in my opinion at least, obvious kind of KD-driven, steady geochemical conditions flow where you're leaving behind a relatively constant concentration of the neptunium. But then we get a nice curvature of the neptunium-4 data set and a huge amount of scatter near the source. These error bars are error bars of triplicate measurements of those. There are error bars on the other data, but they're relatively consistent, so you can't see them. So near the source, there's a huge amount of variability in the concentration of neptunium from the neptunium-4 source. And what we think that's due to is that it's particulate NPO2 coming off that source and transporting a very small distance in the soil. If we look at KD values, near the source, the KD values are in the thousands range versus 10s to 20s for distances 15 centimeters below the source. And they're more comparable to the neptunium-5 lysimeters when we get down here. But near the source, we're up in the thousands. If we go and do microscopy of these samples, this is the pristine original NPO2. This is actually material that was created here on the HB line at Savannah River. This is what it looks like after 4 years in the field. A rather drastic amount of weathering in these materials. We can do XFs and show that at the core of this, the bulk structure is still NPO2, but again, there's an amazing amount of disorder that has grown in with the neptunium-5 preferentially growing on the surface of the particles of these. If we do radiography of the soil and just try to find if there are particles, you can see that it really is preferentially associated with hot spots in the particles that, again, we feel are pieces of these degradation products breaking off of the material to go in and be able to isolate these as very, very isolated particles with neptunium on them. So we set up a second experiment where we just buried another source of NPO2, and the lysimeters near Clemson so we could pull it out and look at it repeatedly. And we're able to get it much closer to that transition. Remember, this is after 4 years of exposure. This is after roughly about 6 to 7 months of exposure. And remember that nice, smooth, pristine crystalline or cubic phase now has this kind of roughness to it. And if you zoom in, you can see these polycrystalline material has alteration along the grain boundaries. This isn't terribly different than seeing UO2 alteration of an isolated fuel particle. And what we believe is that transport of particles is happening by literally particles breaking off of this polycrystalline material. They're not moving far in the soil, but they do appear to be breaking off and at least getting into the first inch or so of soil in here. So our kind of model of this is the neptunium source oxidizing, making some colloidal neptunium that doesn't move very far, but then the rest of it can start oxidizing and transporting as that dissolved, more mobile NPO2, neptunial ion. So I'd like to use the last bit of time in the talk. Now, I mentioned this concept of preferential flow altering the neptunium lysimeters. And so we got a relatively large team together and teamed up with the guys from MI Labs in the Netherlands and started looking at using SPECT and CT imaging as a means of monitoring flow and monitoring reactivity in porous media. So this was the first experiment we did. It's just a column that's roughly about a foot tall. And there's layers of glass beads with some filter papers separating them. And then this is an end-member soil from here at the Savannah River site. It's mostly a kaolinite material. And then every now and then in these layers, we place some capillary tubes within the layer. This image is looking down into that column. We place some capillary tubes so we could see if the flow is going to go through that tube. And so here's an ideal image of that. This is the X-ray CT image of the column, just showing we did, I'll call it an acceptable job of packing most of this, but then you see big gaps like that in the large particles up there. And it turned out actually to be rather useful for us as far as the analysis goes. So we can take the CT, and if we go into the silica flower down in our kind of 250 micron range, you can't see the individual silica flower grains, but we can start seeing our capillary tubes growing in. And then right when we get around, 200 microns or so, you can start seeing the resolution of individual grains of soil, individual glass beads. Then when we get into the soil grains, you can see aggregated clay particles, higher density materials, probably some titanium or iron oxide materials in these. And then you can really easily start seeing the glass beads when they get into millimeter size ranges. So we injected technetium-99m through this, watched the flow going through, and we could start getting relatively high resolution maps indicating both the filter paper, a little bit of absorption onto the Savannah River site soil, as you can see here, and then void spaces. I'll show well over here on the far right corner where a large particle, a glass particle, is sitting in we obviously would expect to not see technetium in this. And so we can generate, this image at relatively high resolution still gives us a spatial resolutions, on the, 500 microns to millimeter scale. It's still not great as far as pore scale processes go. But the thing that we were really pleased with is the real-time monitoring. So this is literally a time-lapse image watching the technetium move through that column, which we were really quite pleased with. And you can see our relatively poor packing job up here, there. And then what's also neat, though, is here's that preferential flow starting to go through. This is just glass beads. This should be as easy as it could get. And yet we get this kind of behavior there. So we can go in and start looking for those unique features indicating different flow patterns going through. And we're pretty excited about this and proud of ourselves for doing that part. And then said, well, glass beads aren't terribly interesting as far as environmental remediation goes. So we tried something a little harder. This is a column packed with soil, and then inside the column, this is the hardest thing we've ever done in the lab, to be honest, in my opinion, is we packed 3 smaller columns inside of one column without a barrier between them, which is actually really hard to do. We had to shake things and use tubes and all sorts of stuff. It's pretty fun. But so there's a rutile titanium dioxide column, a silica glass column, and a titanomagnetite column. This material will reduce technetium in seconds. So what we're hoping to see is slow diffusion into this silica pore space of the technetium as it's moving along parallel to the silica columns and the rutile columns, and then greater attenuation in the titanomagnetite phase. But we didn't know if our flow rate would be slow enough to see the diffusion, so we did put a big disk of titanomagnetite right at the top. So we had to force all the fluid through there. And you can kind of see the image already over on the right, so it's not terribly exciting. But so the disk at the top with the titanomagnetite, this is a spec image of the technetium-99 accumulating in this material. But you can see some preferential diffusion into those side columns. And they're particularly the longer one that has the titanomagnetite in this. So we're starting to get this concept of the processes involved with moving the technetium through, how the flow can impact this. And our goal then, here's the real-time image, and you can see where the majority of the technetium ends up in that upper image. So what we wanted to do is take this and apply this kind of concept to some data from one of these field lysimeters. So this is data from lysimeters that were deployed here at Savannah River site. These had technetium incorporated into a very small puck that was about 1.5 inches in diameter and about 3/4 of an inch thick. And two of them were just made out of cement paste. The other 2 were made out of the saltstone formulation. And this is a plot of the cumulative fraction of technetium in the effluent versus lysimeter number. You can guess from here which one is the grout and which one's the cement. The cement released about half the technetium. The grout retained a lot more of the technetium behind. I should point out the caveat here, this couldn't be further from realistic conditions as far as saltstone is actually concerned. The surface area to volume ratio of our little bitty puck is gigantic relative to the bolts. And the other thing is these are in direct contact with the soil. It's just a puck placed in that soil material. So we weren't trying to test that facility. What we did want to test is a timed release of technetium out of a material in the lysimeters. And so similar to the other ones, afterwards we took the lysimeter and we cut it up. And so this is 0 where the source was. And this is downward mobility, and this is a plot of concentration in the soil. But you can see this rather drastic upward mobility of technetium. And so we know a couple of things about technetium occurrences in saltstone materials. One is that it's going to reduce relatively quickly when it's formed to technetium-4. And so we took these materials and we want to know how stable is that material? How long does it take for the technetium to start altering its chemical state? And so in parentheses here, 117 days, 218 days, are times after we've prepared some samples, taken them to a spectrometer, and looked at the oxidation state and the chemical form of technetium. The second parentheses is the depth in the sample that we were working with. And so we're able to watch this and start looking at this transformation of technetium speciation going through this initially very hydrolyzed species to these partially sulfidized species. And it's the disorder. I don't want to take the time to go through the details of analyzing these graphs, but we can see through the shape of these curves what the chemical form is. And we see after 453 days, it's still transforming through these species. The speciation's still changing, but it's not leaching out of monoliths. It's just changing its chemical form. So what we want to know is, what is the leach rate we need to use over time? So we went into our lysimeters. We know that there's rain coming through. We know technetium can come out and diffuse in all directions depending on the saturation state of the soil here. And then the part of the story, let me just tell the first part of the story, is in this bottom image is showing 0 up to 220 days in the blue of a reactive transport simulation, 255 with a major peak where the source was, and then downward transport of the neptunium in the rainfall. And then 280 days showing the profile that we would expect. The technetium that can release is released and transported quickly through the column. But this is what our data looked like after we finally cut the thing open. So the part that I can tell you now is after 280 days, it got capped in the field. It sat vertical for about 9 more months. Then it got shipped and stored horizontally for about 4 more months. And so the technetium had over a year to continue diffusing out, and then including a 4-month period of time where gravity didn't matter anymore. And even the water in this column could redistribute itself. And so we end up with this final reactive transport prediction of the curve based on the same shrinking core model, the same diffusion constants that I believe I got from Greg Flack in this, predicting it, and coupling it to just a good idea of how flow is happening in these systems that we're quite proud of with this. So in closing, we know neptunium is going to oxidize, we know plutonium is going to reduce, and what we're really interested in is trying to, again, couple these flow and chemistry problems together into, what I'll call a more robust reactive transport model. So, and DOE and pays for most of our stuff, and then Savannah River Mediation supports a lot of the isomers as well. So appreciate the time, and if there's time, I'm happy to take the question.
Thank you, Brian. Yeah, okay, I think we do have just one time for one quick question from David. Yes.
Do you have an opinion on how long the plutonium will take to further break up and become colloidal particles that can actually transport, or the neptunium? Or?
The neptunium, I think, is going to happen on the order of years. The plutonium, I actually believe it will depend on the source term, the original source term. So if you quickly just raise the pH of a plutonium-4 solution, you will inherently make nanoparticles of plutonium. They'll aggregate, but those can be broken apart by just rainwater in the soil. If you take a plutonium oxalate that makes micron-sized primary polycrystalline materials, that's going to take decades. I have no concept of how quickly that will happen. So I believe that there's a history of the source terms. It's another talk to show you all the microscopy data to prove that. But there are differences in those plutonium sources. They all go to PuO2, but the morphology is different enough. Whether or not that'll change the actual release rate, I seriously doubt it. But that could be something within the discussion of uncertainty that took place earlier this afternoon.